Okay, so we've got the equation of motion that our field obeys. I would like to rewrite it slightly. So remember that as a 4-vector, x mu was equal to time and x, whereas x mu lower index was t, and then the spatial components were negative. And this was a general rule. So p mu was the energy and the momentum, but p mu lower is the energy and minus the momentum. I now want to introduce the derivative operator, okay? And the way that d mu is defined is, it is d mu lower is d by dt, and then nabla. Okay, well, let me write out all of the components explicitly. Well, you know what? I'm just going to write that. I think it's clear. So this would be dt, d by dx, d by dy, d by dz. Okay. So notice d mu lower, the spatial components are positive, and d mu upper, the spatial components are negative. Okay. So this is the only vector that you have to worry about this. That's a little bit different. So d mu lower, the spatial components are positive. D mu upper, the spatial components are negative. And you should be able to check this by how d mu transforms under a Lorentz transformation. Okay, so that's a very good thing for you to think about and verify for yourself. It's just an exercise in doing Lorentz transformations. In that case, the Klein-Gordon equation can be written in this way. It can be written as d mu plus m squared phi of x is equal to 0. And this is usually how you will see the Klein-Gordon equation written. That's now written in 4-vector notation. Good. And now, next, I want to make another comment. Let's imagine, thinking about the Klein-Gordon equation. So think about the Klein-Gordon equation as a classical equation. If you wanted to solve the Klein-Gordon equation as a classical equation, this is what the general solution would look like. It would look like, so we'd have an integral d3p over 2 omega p and 2 pi cubed. And then what we would have is some classical amplitude of an e to the minus I p dot x omega p t plus I k, p dot x. And then you would have the complex conjugate of that amplitude, e to the I omega p t minus I p dot x. So this would be the classical solution. Now, how did we get the quantum solution? So this is classical. Here is the quantum solution. So phi of t and x, it looked exactly the same. So integral d3p over 2 pi cubed 2 omega p. The only change is that we didn't have a classical number sitting there for AP. We had an operator. And we didn't have a classical amplitude AP star appearing there. We also had an operator. Now, if you wanted to work out what is the strength of this field, well, the amount of the field, if you like, in mode P, so we can speak about each of these different plane waves as different modes, okay, different ways in which the field can wiggle, the field can oscillate. And we can talk about what is the amplitude inside each of these modes. So the amplitude of the field in the mode, and the mode is labeled by some form momentum, a mu, is the mod of AP squared classically. Okay, just the magnitude of the amplitude squared. Quantumly, it is, so at quantum level, it's given by not AP star, so mod of AP squared. You could think about this as AP star AP. At quantum level, this is AP dagger alpha P. Okay? And that is the number operator. Alpha P dagger alpha P is an integer. It's a non-negative integer. It can be 0. So let me write it by z, and I will put maybe greater than or equal to 0. Okay, so it's some integer which is greater than or equal to 0, but the amplitude of the wave has now become, and the amplitude of the strength of the mode of the field has now become an integer. So when we say we've quantized the field, this is exactly what we've done. The amplitude of the mode P mu in the classical field becomes an integer in the quantum field theory. That's what we've quantized. It's actually the field strength and the field strength for the mode P mu. Good. Okay, so we know what equation the field obeys. We've got some idea about what it meant to go from the classical field to the quantum field. So let me just put down, this is the quantum field. You know, classically, you're used to hearing that the energy got quantized or the angular momentum got quantized. Here, I just wanted to show you what gets quantized in the quantum field theory. It is the amplitude of mode P mu. Good. Next, let's try to start interpreting what our field actually does. So phi of x does something. It's a local field. Well, we know that because it commutes with itself at space-like separations. So it does something at the point x mu. So we now want to figure out what will it do. Well, we can take phi of x, okay, and we can act on the vacuum. Now, remember, the vacuum is the state with no particles in it. So no particles in the vacuum. When phi of x acts on the vacuum, it can do two things. So firstly, it would be allowed to destroy a particle, and that would be the alpha p term that annihilates a particle. Or it could create a particle. And how do you create? That's with the creation operator. Okay, so you could create or destroy. Now, when phi of x acts on the vacuum, there are no particles in the vacuum state. So you can't destroy anything, but you can create. So phi of x acting on the vacuum, what will it do? It will create a particle at position x mu. So the field does something at x mu. What does it do? Well, it creates a particle. Okay, now let's apply a second field. So let's say we've got phi of y onto phi of x naught. Now we know what this is. This state is the state of a single particle at x mu. Okay, we'll continue in a moment.